Hello everyone. So today we'll be solving another LeetCode medium problem, greatest sum divisible by 3. So the problem states that we are given an array of integer nums and we need to return the maximum possible sum of elements of the array such that that sum is divisible by 3. So and the length of nums is given up to 44 and also nums of I can be up to 1e4. So here for example if we have the nums as this, so we need to make the sum divisible by 3. Okay, and we need to maximize this sum. So we'll definitely choose those elements which are already divisible by 3. So for example here we will choose 3 and we'll definitely choose 6 here. Alright, so we have got 9 as the sum. Now we need to choose some rest of the elements such that overall sum also remains divisible by 3. So here the remainder by 3 is 2, here the remainder by 3 is 1, and here also the remainder by 3 is 2. So what we'll do is we need to choose elements such that the overall sum of remainders also remains divisible by 3. Then only the overall sum will also remain divisible by 3. Right? So since here we can see this 2 plus 1 we can make it 3, hence the overall sum will be divisible by 3. So for 2 we have two choices, 5 and 8. So since we want to maximize the maximum sum possible sum, we will take 8 here. So hence the values we will choosing is 1 plus 8. So hence the overall sum values would have 3, 6, 1 and 8, and the sum would be 18, which is the maximum possible here, right? For example, similarly if we have another input like nums is given as 4, so as you can see the divisible means 4% 3 is equals to 1, which is not divisible by 3, right? So since it is not divisible by 3, we will not be able to choose any element, and hence the output here is 0 only. Okay, now let's see another input. So here we have 1 2 3 4 4. So as you can see we have 3 which is divisible by 3, so we'll definitely choosing this. So we have already chosen 3. Now we need to choose uh, some more elements such that the sum of remainders of those elements will still be divisible by 3, right? So here remainder is 1, here remainder is 2, here remainder is 1, and here remainder is 1. Now we can we need to make the sum of remainders as 3. So what we can do here, either pick 1 1 and 1, or what we can do is we put pick 1 and 2. Now if you choose 1 1 1, the sum would be 1 plus 4 equals to 9. And if you pick 1 and 2, then for 1 we will be choosing the maximum element, so it will be this 4 or this 4, so it will be 4. And for 2 we only have a single choice, that is 2, so the element 2 and 4 will be chosen, right? So 2 plus 4 equals to 6. As you can see, choosing in this way is better, as this sum is more, so hence the overall sum would be 3 plus 9 equals to 12, right? And hence the output here is 12 only. So you are seeing here, if we see here, we have rejected some elements, we did not pick 5 here, right? Here we have rejected this element 4 here, here we have rejected means 1 4 4, so here we have rejected this 2 here. So since means why we are rejecting these elements, because some elements disturb the divisibility by 3, right? And that's why we need to remove these elements. Now when we are removing these elements, so suppose, and why it will break the mean disturb the divisibility means either we have already got a sum which was divisible by 3, right? Sum 1. And now when we added this element into this sum plus x, then the overall means new sum 1 plus x, this percent 3 is not equals to 0. So we can think in the direction of we, since the number of elements that will not be choosing will be very less, because since we need to maximize the possible sum of elements, hence the number of elements we will not be choosing in the sum of elements would be means few only. So in in that direction we can think to like only to mean find out elements which will be not be choosing. So for example, here we did not choose 4, here we did not choose 2, here we did not choose 5. Now how do we find out which elements not to choose, right? This is the question. So which elements not to choose? So suppose like we have initially taken all the elements as result, initially taken all elements, and it has a sum like sum. Okay, now we need to like remove some elements such that this sum minus removed will become divisible by 3, right? Now these removed elements we need to find out, and we will remove in a manner such that we will means this has a sum minimized sum, means their sum is minimum, so that the means since we are dividing means subtracting it, so if this is minimum, then only the overall result will be maximum, right? Now the overall sum of all the elements was 3, so there arises three cases, right? Case 1 is sum percent 3 is equals to 0. That means it was already divisible, and since it was already divisible, that means we do not need to remove any elements, because and in that case the sum that we have got will be the possible maximum sum only. So in that case we will be just returning the sum. Okay, now the second case where sum percent 3 is equals to 1. Alright, that means like some elements are disturbing the divisibility by 3 and giving us remainder 1. So that means like let me write a remainder array. So we might have got something like we had elements which were divisible by 3, right? And then some elements which were divisible by means gave remainder 1, and then some elements which gave remainder 2, right? Now we know that suppose we account for remainders 1. So if we need to find the sum, overall sum has a remainder of 1 with 3, we'll either have one element or we'll either have four elements, like because only then only the sum would be means some percent 3 would be 1, or we'll have 7 elements. So we know like since skipping 4 elements is not feasible, so remainder equals to 1, we can skip one element or 4 element or 7 element and so on, right? But what is feasible here? If we like skip 4 elements, is it good? Obviously not, because if we choose these 3 elements as part of sum, since all of these 3 has a remainder as 1, so hence 1 plus 1 plus 1 will make the sum divisible by 3 only, right? So hence these 3 values will not be disturbing the overall sum, only this single one is disturbing the sum of elements. Hence we will only skip one element with remainder 1, right? So hence what we can do is we can like skip the minimum element which has remainder 1, right? Now what if this one was not violating the condition? What if some elements which had a remainder 2 violated the condition? So as we can see, like a single element with remainder 2 cannot make the overall remainder as 1, right? Or suppose if we try to make combinations, then this 1 plus this 2 will again make 3. Hence a single means 2 will not be making the sum as 1. So what if we choose 2 elements with remainder 2? So 2 plus 2 would be 4, which is 4% 3, which is 1. Then we see like if we pick 2 elements or if we pick 5 elements, right? Or if we pick 8 elements, then the sum of elements who had a remainder 2 would make the overall sum give a remainder 4, remainder 1, right? As you can see, like 2 plus 2 is equals to 4. Or suppose if we pick it 5 times, then overall sum would be 10, and 10 mod 3 equals to 1. So then we can see, like, first case was this, and we can like only skip two elements with remainder 2, right? So we will just simply skip the two minimum elements, two minimum elements which has remainder 2. And now what if, like, both of these conditions are satisfied? Like, we have also have some elements with remainder 1, and we also have some elements with remainder 2. So obviously we'll be just choosing the minimum of them, right? So either minimum of skip 1 with remainder 1, or skip 2 with remainder 2. Hence it will be the minimum of this min element, min of suppose remainder 1, okay, and it will be min 1 of remainder 2 and min 2 of remainder 2. First min and second min with remainder 2. So we'll be taking the sum of them, and this will be the scenario in this case. So I hope, like, you get, either we will skip one element with remainder 1, or we'll skip two elements with remainder 2, so that the overall remainder still remains as 1. You might wonder, like, what if we skip one single one and one single 2? This will not be feasible, because if you skip this element and skip this element, you are already means decreasing the sum only, because if we choose them, 1 plus 2 will become 3, and the sum will be still be divisible by 3. Hence we can only skip either all means either some elements with remainder 1, or we'll skip either some elements with remainder 2. So this is the approach that we will be following. So hence in the case 1 we just return the sum. In case 2 we will be finding out this value and finally return sum minus. So suppose this is mini, so sum minus mini, right? Now comes the third case, where the overall sum gives us a remainder of 2. So in that case, again we can see, like, since the overall remainder is 2, so how many elements of remainder 1 can we skip? We can skip 2 elements, right? So that the overall remainder still remains 2. And for remainder equals to 2, we can skip 1 element. So what will be the case here? In this case, here we skipped 1 element and 2 elements of remainder 2. Here will be, here what we'll be doing is, it will be minimum of 2 elements of remainder 1. So it will be, so suppose min 1 of 1 plus min 2 of 1, and comma the minimum element of remainder 2, and then finally return sum minus min, right? So these are the three cases that we need to handle. The main observation was to identify, like, we are removing some of the elements, and we will remove as few elements as possible. So hence we try to think in that direction, and we find out, like, we will either remove two elements or one element from the given array to make it divisible by 3, and we just identified what elements we need to remove based on different cases. And yeah, so let's, like, try to see the code here uh, of this approach. So here I have like created a vector rem, which, like, rem of 0 contains a vector with all elements having remainder 0. Rem of 1 will be also be another vector, and rem of 2 will also be another vector. Okay, now why am I creating this vector? So that I can segregate the remainders and then find out the minimum or the two minimum values from rem 1 or rem 2, right? So this is what I have done. Remain of it percent 3, we'll just push it in this vector or this vector or this vector, and I am taking this result to maintain the overall sum, right? Now I will show. So we have three cases. Result percent 3 is 0, so no need to remove any elements. Result percent 3 equals to 1. Remove one smallest element with remainder 1, or remove two smallest elements with remainder 2 and take minimum of them. Or we have result percent 3 equals to 2, so we will remove two smallest elements with remainder 1, or remove one smallest element with remainder 2 and take minimum of them. So if result percent 3 equals to 0, we will simply return the result. If result percent 3 is 1, so we need to remove one smallest element with remainder 1, and remainder 1 values are present in rem of 1 because this was a vector of vector. So if rem of 1 of size is greater than 0, that means there exists some elements. We'll find out the minimum element. And how we are finding out this minimum element? We have sorted the values. So either we can sort it like this will take the complexity of n log n, means overall complexity it will make n log n. So since we are only need to find the minimum element or two minimum elements, we can means find it out using two variables also, int mini and second mini. So this is also feasible, means sorting it would make the code look cleaner. That's why I have done this. You can also like avoid sorting and just find out these two minimum by iterating the loop and maintaining these two variables. Now, so this remove the minimum element we have find out which will be present at the 0th index, and two minimum elements we need to find if only if the remaining two of size is greater than or equals to 2, then it would be the two elements at that start of rem2. So it will be rem2 of 0 comma rem2 of 1. And else why I have taken this int max, so that even if like some elements with 1 are also present and some elements with 2 are also present, right? And suppose this condition will execute when we do not have any element of with remainder 1. So this portion will not be there, only elements with remainder 2 will be there. So hence this condition is there so that we do not account removal of 1 in any case. And this will, if this condition is not true, then this condition will definitely be true because the overall sum is giving us remainder 1. Alright, so we'll either have two twos, or we'll either have five twos, or we'll have eight twos, and so on, right? And if there is like no twos present, like this portion is not present, then we will either have one threes or four ones, or we will have seven ones or 10 ones, and so on, right? Because the overall sum has a remainder 1. And finally we will be just returning the result minus minimum of those two values. And the same we are following, we are like finding out two smallest elements with remainder 1. So it will be rem1 of 0 plus rem1 of 1, else int max we set for this condition where one of the means values are missing, and find out the smallest element with remainder 2, and then return the result minus min of rem1 plus rem2. And we can see like we can also avoid this sorting thing, just maintain two variables and find out these two minimum values. So the approach can be of the order of n log n or big of n also. Now another approach, like this was the greedy approach, right? So one more approach that we can discuss here is like, since this means after observing this problem, you might see like a single element can either be chosen or not chosen to be part of the sum, right? So we see that each element has a choice. Each element has a choice, right? Means either pick or not pick to be part of the sum. To be part of sum. So since each element has a choice of picking or not picking, we can like think of DP approach, right? Because what we do in DP, each if we have independent choices for each element, then we can try thinking of dynamic programming approach, and maybe like try to see what means what states will be changing here, and then try to find out the result on the basis of that. So suppose like we what states are changing here, we will definitely iterate through the array, so we'll definitely have dp of index. Now along with that we also need to maintain the current sum, right? The current sum that we have. Okay, so this will have like current sum. And since like if we maintain the overall current sum, then since values are till 1e4, then 44 into 1e4, it can go up to a large value. Hence we maintain current sum percent mod 3, so that the overall sum means this value remains between 0, 1 and 2, so that we do not get like means it will be 1e4 and then it will be 88 if we do not do this mod. Hence we are doing this mod. So this state will be of the order of n cross 3 only, right? And what does it represents? It represents like maximum sum by choosing, means maximum sum from first, means air of 0 to index elements with, means overall sum with sum as sum percent mod as current sum. Alright. So this picking and not picking means this will be what will be the DP representing. And now comes the two cases of like pick or not pick. So how will the states be changing? So suppose like I call the function for call the memo function for index 0 and current sum is 0. Okay. Now how the states will be changing? So represents the index and this represents the current sum. So if we pick the value, then it will be dp of index comma current sum. What it will be? We'll be adding the current value of the sum, current value of the at that particular index. So it will be this plus what? We'll call the function for dp of index plus 1 because we are moving from index 0. So we'll call the function for dp of index plus 1 and the current sum will change by current sum plus nums of index. So it will be current sum plus nums of index, and since we need to take mod with 3 as well. Alright, so this is the scenario of pick, and if we try to like skip the current element, then in that case dp of index comma current sum would be nothing but we just skip to the next index. Okay, and in the end what we'll do is dp of index comma current sum will take max of pick comma skip, right? So we observed like each means element had an independent choice of being chosen or not chosen. Hence we tried to think of DP. Then we identified like what states can change here. So definitely index will be one part of it. And since we also need to maximize this sum, so we also need to maintain the current sum, so that we only account in the end. In the end, we only account those values which are the current sum means greater equals to 0. That means divisible by 3. Divisible by 3. Hence, that derives us to what will be the base case here. So, if index reaches n, alright, that means we have like iterated the entire array and we have the index points to here on now. So, in this case, after the end, what means the current sum that we have should be 0, right? It should be 0, so that the sum that we have chosen so far represents that it is divisible by 3. Alright, then only we will account it to be a part of our answer of maximizing or not maximizing. Hence, if current sum is equals to 0, then we will simply return 0. Alright, because we have already added this nums of index here, so the values will keep on increasing and will not disturb it. But if the current sum is means is equals to 1 or 2, then what do we do return in this case? So since we like want that this value should not be representing a sum which we can choose, right? So either we can like return a very small value so that the overall sum becomes negative, and if it becomes negative, then uh, we'll like not account it in this max of pick comma skip. Okay, because one of the values will be negative. So in that case we can either return like int minimum. Alright, so this will be the base case of our recursive function, and we'll be updating it using these two transition steps. And yeah, let's move on to the code once, and we'll see how we have implemented it. So we have this 3D DP array, means 3D n cross 3 vector. Now we will call for index 0 and current sum 0, right? And what it represents is maximum sum by using array 0 to I with sum percent 3 is equals to j. Okay. Now the base condition was when we reach the end, if current sum is 0, then we return 0. We do not means this validate the sum, and else we return a very small value so that the overall sum becomes negative, and it does not gets accounted in this function, in this max of pick comma skip. Alright, if it was already accounted for, so this we have memoized the TP, then we'll simply return it. Else we'll pick this element. So for picking, it will be nums of index plus, we'll move on to index plus 1, and we'll increase the current sum by nums of index. And if we skip it, then we just simply move to the next index and the current sum remains the same. In the end, we'll be just taking the max of pick comma skip. So this is the DP approach that we'll be following for this problem. This will be of the order of n cross 3. Okay, the number of DP states that we have, and the space complexity would also be big of n cross 3. Okay, now now how, like since we since I have told you the memoization approach, it is like always means everyone wants to see the tabulation solution and then see if space optimization is possible or not, right? So I'll be teaching, means telling you that code as well, so that like you have an idea of how do we move from this memoization to tabulation, and see whether the space optimization problem means possible in that solution or not. So I hope like this transition is clear here in the memoization, because based on the transitions only we decide like how we'll be writing the tabulation code. So I will show you the tabulation code and like help you decide step by step what means how whether to move the indexes from the start or the end. And if you hear it means efficiently, you will get the approach. So just be with me for a minute. So this is the approach. Now we call the function for memo of 0, right? And index, the maximum value that index will ever achieve is nums dot size. That means the maximum value that any index will receive is n. Hence we need to, if while writing the tabulation approach, for each state we need to decide the size of dp. So since index is taking maximum n, hence we need to create a dp of n plus 1 size, right? As well as this current sum will only take the maximum value till 0 1 2. Hence size 3 is feasible here. Hence we have created this vector of size 3. Now comes the base case. What about the base case? So we see when index is equals to n, we have these two conditions. So if current sum is 0, then we have return 0, else we have return int minimum. So this is what we will do. If the sum is 0, then we'll put dp of n comma 0 equals to 0, because we are returning 0 here. And in other two cases, when sum is 1 or 2, we'll just put int minimum here, right? So this is how we move from memoization to tabulation. Here the base case was in form of means recursion function. This is what we are converting it to normal tabulation. So I hope this base case is clear, and why we have taken this n plus 1 here, because the base case had index equals to nums dot size. So in the worst case, index would reach n. So hence we have created a vector of size n plus 1. Now we'll be filling this table. Now how do we decide, like how do we move these indexes? Means either we can start from n minus 1 or start from index equals to 0, right? in the loop means that we'll be using to write the tabulation code. So how do we decide how to move the indices? So as you can see, like here I call the function for index 0 and current sum 0, and in each transition we are moving to the next index, right? So we are moving from index to index plus 1, right? Now we know that index equals to n, the result is already calculated in dp, right? For index equals to n, the result is already calculated. We need to find out the result for index equals to 0, right? So how do we find out? So if for index equals to 0, we need the result for index equals to 1. For index equals to 1, we need the result for index equals to 2, and so on till n minus 1 and n. So to calculate the result for n minus 1, we need the result for dp of n. Then for the previous values, we need the result for next values. So if we try to see this, this tells us that we need to calculate the results in the reverse order. Alright. So we need to find out first dp of n minus 1, then dp of n minus 2, and so on till then only we'll be able to find out dp of 0 in the end. Okay. So that's why we have started this loop from the reverse order, means index equals to n minus 1, so that we have the result will have the next, means index plus 1 results available to calculate the index results. Okay. And now how we can move this second loop, like from either from 0 to 3 or 3 to 0. So means since this current sum can change to any value, like suppose it was 1 before, and after that this nums of index was uh, suppose 3, suppose 4, then becomes 5, and 5% 3 equals to 2, and suppose it was 2 before, and then we added 2 again, nums of index, so it will become 1. So this current sum does not has a fixed pattern of like either moving from 0 to 1 or then 1 to 2, does not have an increasing or decreasing function, right? So hence we can choose, means any loop will work here, either we can move from 0 to 3 or we can move from 3 to 0. All right. So this is what we have done here. We move from 0 to 3, but we can also move from like current sum equals to current sum greater than equals to 0. Okay, we can also do this as well, because current sum does not depend on means only this index plus 1 thing we only need to pre-compute for the next index, right? If we have the values for dp of n for all the states, then this current sum does not matter. Okay. Now we have the pick condition where we will be picking the current element, and the state will be dp of index, the same what we did here. What we call pick was nums of index, so here also nums of index, then memo of index plus 1, so we call dp of index plus 1, and the current sum was current sum plus nums of index percent 3. So this is what we have done here, same. And in skip case, what we call index plus 1 and the current sum remained the same, so we did the same, dp of index plus 1 and the current sum remains the same. And finally we'll update the dp with the max of pick comma skip, and which state will be storing the final answer, the memo function that we call for 0 comma 0, hence the final result will also be stored in dp of 0 comma 0. So this is the approach for tabulation of like the complexity, and the space remains the same, but this is the tabulation way of writing it. Now like we'll see if we can space optimize it. Okay, whether space optimization is possible or not. So for finding out whether space optimization is possible or not, we need to see means make some observations. So here we can see like the dp of index is only dependent on dp of index plus 1, right? So dp of index only depends on dp of index plus 1, right? So suppose we have the entire dp array of n cross 3. Okay, and so on. Now this is dp of index vector, and this is dp of index plus 1. So we see that this row is completely dependent on this row. So this means the calculation for this current dp state only depends on these three values that we have, this and this, and using these three values only we'll be able to calculate the result for this row, right? So if the current dp does not depend on a lot of rows, then in that cases space optimization is possible. So this is generally what we need to find, like whether the current dp depends on, if this had dependent on like index plus x, index plus y, some variable values, then optimizing on the basis of a space would not have been possible here. But since it is only dependent on index plus 1, then we can optimize on space. And how will we optimize it on space? Instead of dp of index, we can just maintain these three variables. So either we can create a vector of size 3, or we can maintain abc three variables which will be storing the values for each column. So we can represent these values by a, b, c. And now for calculating the a dash, b dash and c dash of this row, we'll only need the values a, b and c. And once we have calculated these a dash, b dash and c dash, the new abcs means for the previous rows, this will become the new abc. So new a will be a dash, b equals to b dash and c equals to c dash. New values would be this, and for calculating these values we will be using the results of these results. So we see like we only need the result of these three variables to calculate the result of any index. Hence instead of using a dp of index means dp of size n, we can limit it to size 3, and hence in that manner we can like space optimize here. So this is what we generally try to see to identify whether a problem can be space optimized or not. Now let's see the code, and I will be just showing you how we transition from like this tabulation approach to the space optimized one. So everything will remain the same. This dp of n plus 1 will not use, instead we will just simply use dp of 3. Okay, so we create a next dp of size 3. We have removed this n plus 1 here. Now again we will write the base case. So what was the base case? It was n comma 0 equals to 0. So we have removed the n. So next dp of 0 equals to 0, and then dp of n comma 1 and 2 was int min. So since we have removed the n, we will just simply write next dp of 1 and next dp of 2. Okay, here we had dp of n and dp of n comma 1 and n comma 2. Here we will simply write 1 and 2. Alright, now for this entire dp, we have find out the result for dp of n, which is stored in next dp of 3. Now we need the result for this row, right? So to calculate the result for this row, we make a new current dp vector to store the result for this row, which will also be of size 3. Okay, and now for calculating the results of this this row, we only need the result of this row, which will be stored in next dp of 3. Hence to store the current result of this row, we have calculated this vector, and now the loop remains the same what we have done in normal tabulation, and this everything remains the same. Just what will change is, here we had dp of index plus 1, and now the result of dp of index plus 1 is stored in next dp. So we'll just simply replace dp of index plus 1 with next dp, and here also we'll just simply replace dp of index plus 1 with next dp, and everything else remains the same. And here we'll replace dp of index, since it denotes the current row, so it will be current dp. Okay, and finally what we'll be returning is, I will show you. So we see we have replaced the dp of index plus 1 with next dp, and we have again replaced dp of index plus 1 with next dp, and will dp of index has been replaced with current DP. Just these three changes has been made to the previous code, and we have created this new vector here, and everything else remains the same. And after we have calculated the result for this row, to account means to find out the result for previous values, we'll update next with this result. So we'll update next DP to current DP, so that we can calculate results for previous rows as well. Okay, so hence the next DP will be current DP. And what will the final result be storing in? So in the end, we'll like for this row, in the end this thing will execute. Hence the result that we have calculated in current DP of this, so either means both current DP as well as next DP will be storing the result. And what we need to return is DP of 0. So since we need to return DP of 0, we can simply return next DP of 0. Means we can replace this with next DP. Okay, so hence we can return next DP of 0. So this is the code for like constant space time, and the space complexity will still remain the same. We cannot further optimize it, but this is how we generally move from memoization, then to tabulation, and then to space optimized tabulation. I hope like the entire idea is clear to you. You can like maybe rewatch the video to get an understanding into your mind. And yeah, and also like we see how we moved from this greedy approach to how dynamic programming can be applied here, because we had choices for each element of getting picked up or not getting picked up. So this is the entire code, means entire logic and approach for this problem. I hope like you get all the approaches, and if you have any doubts, feel free to comment down and I will be happy to respond. Thank you for watching.